Hello. In the first lecture, we have discussed Maxwell equation in differential form and their derivation. So today we will discuss Maxwell equation from differential form to integral form. So Maxwell equation in differential form. The set of four equations are div d is equal to rho, which is Gauss law. Here d is the electric displacement vector and rho is the volume charge density, or you say free charge density. Second, divergence of manifold induction is 0. Third, Corley is equal to minus del V by del T, which is Faraday law. And fourth, Corl H is equal to J plus del D by del T, which is Ampere's law with Maxwell's correction. So differential form can be converted into integral form by using Gauss divergence theorem and Stokes law. So divergence of D is equal to rho. It can be converted to surface integral of electric displacement, that is equal to Q, or you write Q enclosed. Second, divergence of B equal to 0, that can be converted to surface integral of manifold, that is equal to 0. And third, Corley equal to minus del V by del T can be converted into line integral of electric field intensity is equal to minus time rate of magnetic flux. And fourth one, that is del cross S, can be converted into line integral of manifold intensity, which is equal to current enclosed plus d by dt of surface integral of electric displacement. First, integral form of first equation. The differential form of first equation is div d is equal to rho. Now integrating over a volume V, that is div d tau is equal to volume integral of rho d tau. D tau is the volume element and this is equal to Q. Now we apply Gauss divergence theorem. The volume integral in the left hand side can be converted into surface integral. So surface integral over a closed surface. So this is d dot ds or n cap ds. So ds vector, that is equal to Q. So this is the integral form of Maxwell first equation. Then second, integral form of the second equation. The differential form of second equation is div b equal to 0. Now integrating over a volume V. So integral over volume V, that is div b d tau is equal to 0. Now applying Gauss divergence theorem. So the left hand side can be converted into, that is surface integral over a closed surface. So b dot n cap ds or ds vector, this is equal to 0. So this is the integral form of second equation. Then third equation, that is integral form of the third equation. The differential form of third equation is curl E is equal to minus del B by del T. Now integrating over a surface. So surface integral of curl E dot ds vector is, that is minus surface integral of del B by del t dot ds vector, which is equal to minus d by dt of surface integral of B. Now we apply Stokes theorem. The left hand side can be converted to a line integral by using Stokes theorem. So this implies line integral of electric field intensity, that is equal to minus d by dt of surface integral of B. So surface integral of B, that is here B dot ds, that is magnetic flux. So line integral of electric field E is equal to minus d phi by dt. So this is the integral form of the Maxwell's third equation. So better we write in integral form, that is E dot dl is equal to minus d by dt of surface integral of B dot ds. So this is the integral form of the Maxwell's third equation. Next, integral form of Maxwell's fourth equation. Maxwell's fourth equation. The differential form of Maxwell's fourth equation is curl H is equal to J plus del D by del T. So integrating over a surface. So surface integral of curl H dot ds is equal to surface integral of J plus surface integral of del D by del T. We know that surface integral of current density is equal to, that is I. I is the conduction current. So now we apply Stokes theorem to this left hand side of this equation. So that can be, this can be written as, that is line integral of magnetic field intensity is equal to I plus surface integral of del D by del T. So this is the integral form of Maxwell's fourth equation. What is the physical meaning of this Maxwell's equation? So first equation is, that is the flux of D vector through any closed surface is equal to the net charge enclosed by the surface. So this is the physical meaning of the first equation. And the second equation is that the flux of magnetic field through any arbitrary closed surface is equal to 0. It shows that there is no magnetic charges. Monopole does not exist. Monopole does not exist. In other words, magnetic monopoles are non-existent. The lines of B have neither beginning or nor end, as net magnetic flux through any closed surface is 0. And the third equation, that is implies that the circulation of vector E vector around any closed contour is equal to the negative time derivative of the magnetic flux through arbitrary surface bounded by the given contour. And the last one is, that is, that equation implies that the circulation of magnetic field intensity around any arbitrary closed contour is equal to the total current, that is conduction current I plus displacement current through an arbitrary surface. Further, it shows that conduction current and displacement currents are possible sources of magnetic field. So these are the physical meaning of the Maxwell's equation. Thank you for watching.